chemists have created much of the modern world. If we look around, we see curtains, we see plastics, we see metals, metallurgy, we see adhesives, we see lacquers, we see paints. In the computer, we have semiconductors, silicon, glasses, transparent plastics. Where would we be without these? It's interesting to recognize that we would be a long way back. We couldn't have mobile phones, we couldn't have cameras, we couldn't have many of the things like refrigerators without these materials. And chemists have made all of them. I mean, not just the pharmaceuticals. They've made much of the modern world possible. And I think it's really forgotten that these materials weren't there. If we're going to talk about chemistry, we should go back to the earliest times. And it looks as though the Greeks had a reasonable idea. They thought of atoms, indivisible, small particles. They had no idea how small they were. But they also had something rather interesting, and that was the feeling for symmetry. Plato had come up with 4 structures, and then the 5th was discovered, the 5th Platonic structure. It was this. It was basically the dodecahedron, which had pentagonal faces. Now, although that was a simple idea, and they had these thoughts of air, fire, earth, and water as the main elements, the idea of symmetry is so fundamental to the sciences that it's interesting that, in a sense, in the spirit, they were very close to the way things actually are, because we know in atoms they have symmetries. The way in which neutrons and protons are put together have some symmetric structures and some patterns. Well, it was a long time before much progress was made, and then people like Newton, famous people, thought they could transmute the elements. They could probably make gold out of silver or lead and these sorts of things, and that was alchemy. And out of alchemy sprung chemistry. And I think the first ideas of this came from things like soap, where they were able to make useful materials. And I guess the first major chemist was Lavoisier. Lavoisier is an interesting character, as well as really showing that oxygen and hydrogen were really elements and naming them. He also was a tax collector, and he fell out of favor, and Marat accused him of some fraud, and he was guillotined.
Antoine Laurent de Lavoisier nasce il 26 agosto 1743 a Parigi. Fin da ragazzo mostra una vocazione per le scienze. Si laurea in legge alla Sorbona, ma non smette di interessarsi alla chimica, che al tempo era ancora un sapere intriso di credenze magiche e alchemiche. Lavoisier, grazie alla guida dei migliori maestri del tempo, applica invece ai suoi studi un grande rigore intellettuale e si dedica all'osservazione e alla sperimentazione in laboratorio. I risultati del suo impegno non si fanno attendere. A soli 25 anni, Lavoisier viene eletto membro della prestigiosa Accademia delle Scienze. L'anno successivo, lo scienziato fa il proprio ingresso anche nella vita pubblica francese come esattore. Anche nello svolgimento di questa attività, Lavoisier introduce lo spirito riformista dell'illuminismo, di cui condivide gli ideali, e cerca di produrre miglioramenti nel sistema monetario e fiscale del regno. Si applica anche all'uniformazione dei sistemi di misurazione, aiutando a sviluppare e introdurre il sistema metrico decimale in tutta la Francia. Pochi anni più tardi, grazie anche alla collaborazione della giovane moglie, ottiene i primi importanti risultati sperimentali, studiando il meccanismo della combustione. Gli esperimenti di Lavoisier sono tra i primi di tipo quantitativo e gli consentono di giungere a una formulazione fondamentale nella storia della scienza, la legge di conservazione della materia. Anche se la materia cambia il suo stato nel corso di una reazione chimica, la quantità è la stessa all'inizio e alla fine di ogni reazione. È grazie a questa ed altre scoperte rivoluzionarie, come la nuova nomenclatura degli elementi chimici, che Lavoisier è oggi ricordato come il padre della chimica moderna. Il suo Trattato di chimica elementare, pubblicato nel 1789, è considerato il primo testo scientifico in questa materia. Nel 1794, a seguito della recente rivoluzione, viene accusato di corruzione per via dei suoi rapporti con il precedente regime e, dopo un processo sommario, condannato alla ghigliottina. Muore così decapitato sotto gli occhi della moglie. Sono celebri le parole con cui il matematico Lagrange commentò l'evento. È bastato un momento per tagliare quella testa, e forse non basterà un secolo per generarne un'altra pari alla sua.
Perhaps Priestley should be mentioned as well, although he still believed in what was called the phlogiston theory, that when something burned it gave off something called phlogiston, which Lavoisier had shown was quite incorrect. He was the person who discovered oxygen. He was an interesting character too. He had a sort of curious religious leanings and beliefs, and his laboratory, I think, in Birmingham was burnt down. And he fled to the USA, and in fact, the most prestigious medal of the American Chemical Society is the Priestley Medal, who spent most of the rest of his life, I think, in Pennsylvania. There are other important breakthroughs, and one of them was by Boyle, which is Boyle's law, which in its final form, the gas law. And the sun's gas is balanced according to the gas law, and that balance actually enables the sun to emit energy roughly the same sort of production rate over something like 4,500 million years or 5,000 million years up to now, and should go on for another 5,000 million years. Well, those were the very early days, and I think perhaps we should think now the next major breakthrough was that of Dalton. Dalton was also an interesting character, and he made, I guess, the first major breakthrough with regard to atomicity. He conjectured that as it didn't matter how much material you had, the ratio of carbon to oxygen in carbon dioxide was always the same. He basically drew the conclusion that that meant that all matter was consisted of atoms and molecules. And in fact, his drawings of CO2 with carbon and two oxygens are essentially the drawings that we use today. He got a few things wrong because he assumed that in the case of water, the most abundant species would have just one hydrogen and one oxygen. So he, instead of H2O, he got HO. And in ammonia, he got NH instead of NH3. But by and large, that was a massive breakthrough. And I think from that point onwards, the atomic world or molecular world of chemistry really came to the fore. And I think in some ways it separates chemists, and perhaps physicists as well, from the rest of the human race, because when they think about water, they just think of something they drink or something that they have alcohol in it, or liquids and solids, or just like that. But to the chemist, the atomic and molecular perspective is absolutely crucial. And it gives us a a deep feeling for what materials are, how they behave, and why they behave in the way they do. Perhaps as much as anything else, Avogadro was important because when he came up with his perspective on how small these things were and how many molecules or how many atoms there actually are in, say, a cubic centimeter, which is Loschmidt's number and Avogadro's number in the case of water, 18 grams, we then realized just how small atoms actually are. And that is at the nanometer scale. And of course, today we've heard of nanotechnology, nanoscience. And so basically, if you want to say who is the father of nanotechnology, well, you'd have to say that it was probably a combination of Lavoisier and Dalton, and I would say Avogadro.
Alle radici della chimica moderna si trova l'alchimia, una forma di sapere a cavallo tra la scienza e la magia, che ha conosciuto importanti sviluppi sia nelle civiltà orientali sia in quelle occidentali. Un'importante scuola di alchimia sorgeva ad Alessandria d'Egitto nel II secolo a.C. La scienza alchemica inseguiva 3 scopi principali: la trasmutazione dei metalli per la creazione di elementi preziosi come l'oro, la scoperta di un rimedio per le sofferenze dell'umanità, la ricerca della lunga vita con i famosi elisir. Tra l'antichità e il Medioevo, l'alchimia si sviluppò in ambito bizantino, nella civiltà romana, ma soprattutto nel mondo arabo. Dalla lingua araba, infatti, derivano termini come alambicco, alcalino, alcol, elisir, nafta. Con le crociate gli europei si impadronirono anche di questa scienza e la portarono in Occidente. Nel Rinascimento, con Paracelso, l'alchimia divenne sapere medico, collegando al corpo umano i 3 principi primi della materia, ovvero sale, zolfo e mercurio. Le teorie di Paracelso avranno una grande influenza fino al secolo di Lavoisier e contribuiranno alle innovazioni della chimica analitica, ma attraverso una lenta spoliazione della loro veste metafisica e spirituale. La chimica moderna si affermerà progressivamente come scienza autonoma, mentre l'alchimia proseguirà il suo cammino. Ma il sapere millenario dei metalli e degli elisir lascerà in eredità alla nuova scienza un importante bagaglio di osservazioni e scoperte.
I think the development of scientific philosophy, which for me is the search for truth about the universe, basically nature and the physical world, without that evidence-based attitude that dates back to Galileo, I think nothing is of any value. People have personal ideas of these things, and for me they are irrelevant without evidence. And chemistry is definitely something about evidence, about the way things work. For instance, cooking is basically chemistry. And it's very interesting that it's very complicated, but yet we can actually make a souffle. Well, I can't, but my wife can. But if it doesn't quite work, the next time you change the temperature a little bit, you leave it longer, or this. So very complex processes can be controlled by, and in some ways, very crude strategies. And in a sense, that's how chemistry developed. Now, for me, science is about very simple underpinning concepts, underpinning massively complicated things. And I think the understanding of chemistry at that deeper level really starts with Mendeleev. Perhaps Newland and his law of octaves, eight seemed to be important. But when Mendeleev came along, he came up with his periodic table in which the first row had 2 elements, the second row 8, and then 18. And there is a pattern here. It's an obvious pattern in some ways, but where does it lead us? Well, it leads us to an understanding of the way that science should work. And that is that you should have a concept. I call it my 4 out of 5 rule. If you have an observation, or you make an observation, and you have some theory underpinning it, then that theory must predict something. And then you must look and to see whether that prediction is correct. If 4 out of 5 predictions are correct, then your theory is almost, and I insist on making sure you recognize almost, certainly right. And if only 1 out of 5 of your predictions fits, then you're almost certainly wrong. And that's a damn good rule, and it works pretty well. Now, in the case of Mendeleev, it's a perfect example of this, because he had this periodic table and he fitted the elements basically along with their masses that he had a reasonable idea of. And he found there were gaps. For instance, there was no element in the essentially the next row after silicon. He couldn't find an element, a known element there. So he predicted that one day something called ecosilicon would be discovered. Okay, and in fact, in time, germanium, which we now call, which he called ecosilicon, was discovered. And basically, he actually predicted about 4 or 5 elements that were missing from his table that were subsequently discovered. A very beautiful example of the way science works.
Dmitri Ivanovich Mendeleev nasce nel 1834 in Siberia, lontanissimo dai centri della scienza dell'Ottocento. Ma grazie alla determinazione e all'intraprendenza della madre, che desiderava avviare il figlio agli studi superiori, nel 1850 si trasferisce a Mosca. Qui l'università non accetta l'iscrizione di Dmitri e i Mendeleev sono costretti a spostarsi ancora più a ovest, a San Pietroburgo, dove la madre riesce finalmente a iscrivere il figlio alla facoltà di fisica e matematica. Mendeleev intraprende così una rapida e feconda carriera di studente e ricercatore. Nel 1859, con una borsa di studio, si reca ad Heidelberg, dove insegnava il grande Bunsen, e lì si dedica intensamente al lavoro in laboratorio. Torna in Russia nel 1861 e pochi anni dopo viene nominato professore di chimica generale all'università. Nel 1869 pubblica la prima edizione della sua celebre Tavola degli elementi. Mendeleev si accorge che gli elementi chimici, in base al peso atomico e alla valenza, possono disporsi secondo un modello ripetitivo, ovvero che certe proprietà chimiche e fisiche variano in funzione del crescere del peso atomico, ripetendosi secondo andamenti particolari dopo ogni alogeno. Con grande intuizione, lo scienziato comincia a collocare all'interno di uno schema tutti gli elementi conosciuti, secondo una legge di ricorrenza periodica delle proprietà, e riserva degli spazi vuoti, ipotizzando l'esistenza di elementi ancora sconosciuti, in base alle proprietà di quelli che si trovano sopra e sotto nella tavola. Lo scienziato viene promosso capo della Camera dei Pesi e delle Misure, che ben presto diventa un centro scientifico con compiti di ricerca e di controllo, e con l'obiettivo strategico di unire la Russia alla civiltà industriale dell'Europa, ma senza tradire la cultura russa. A un anno dalla sua morte, che avviene nel 1907, grazie alle scoperte collegate alla tavola degli elementi, Mendeleev riceve il premio Nobel per la chimica.
Now, for me, a revelation came when I started to look into quantum mechanics. Quantum mechanics obviously goes back a long time in this, as far as this century is concerned, because it goes back to certainly Planck, and then Einstein, then Schrödinger, Bohr, Max Born and Heisenberg and Dirac. But the most important aspect from quantum mechanics for me was that the numbers 1, 3, 5, and the next one is obviously 7, a number pattern, underpin the periodic table. And that can be understood in the following way. That if we take the number 1 and multiply it by 2, we get the first two elements of the periodic table. Then we take 1 plus 3, which is 4, times 2, we get 8, and there are 8 in the next row of the periodic table. And then you take 1 plus 3 plus 5, which is essentially 9, and multiply that by 2, we get 18, and we get the next row, the 18 row of the periodic table. And what is really beautiful about quantum mechanics is that it shows us that the numbers 1, 3, 5 underpin the periodic table, something really beautiful, a number pattern of great simplicity that we now understand. And the periodic table of Mendeleev basically underpins, or in some ways explains, the whole of chemistry, okay, essentially the whole of biology, and therefore the whole of life, and basically some of the most important aspects of physics. In fact, physics, of course, is that overarching philosophy of nature and the physical world. But chemistry is that massive part of it that pertains to us, the world at room temperature, of materials, of biology, and other things like that.
Il primo passo nello sviluppo della chimica moderna è stato l'individuazione dell'atomo. All'inizio dell'Ottocento, l'inglese John Dalton avanzò l'ipotesi che la materia fosse formata da atomi. Fu un altro inglese, Ernest Rutherford, ad ipotizzare che gli atomi fossero costituiti da un nucleo a carica positiva e un guscio a carica negativa. Fu il danese Niels Bohr nel 1913 a proporre la teoria degli elettroni che viaggiano in orbite ben definite intorno al nucleo dell'atomo composto da protoni e neutroni. Protoni e neutroni hanno una massa quasi uguale, mentre gli elettroni hanno massa 1836 volte più piccola. Gli atomi di elementi diversi si distinguono in base al numero di protoni, il cosiddetto numero atomico. L'idrogeno, con un solo protone, è l'atomo più piccolo. Uno dei più grandi è l'uranio, con 92 protoni. Combinandosi tra loro attraverso legami chimici, gli atomi formano le molecole, le più piccole particelle di una sostanza che ne conservano tutte le proprietà. Quando le molecole sono costituite da atomi uguali tra loro, come nel caso dell'ossigeno, si parla di elementi, quelli contenuti nella tavola periodica di Mendeleev. Quando invece gli atomi sono diversi, si hanno i composti. Il sale da cucina o cloruro di sodio, per esempio, è un composto di cloro e di sodio. L'ammoniaca è un composto di azoto e idrogeno.
Probably the next topic that needs to be addressed is structure. I think important ideas of structure were absolutely crucial to an understanding of chemistry, and they didn't come easily. I think perhaps they just didn't even think that at the start that structure of molecules was important. So I think breakthroughs in recognition that crystals might have something to tell us about the structure of the molecules from which the crystals formed are really quite important. And people like Pasteur recognized that there were left-handed and right-handed, or chirality, where there was some stereochemical issues to be resolved. I guess Van 't Hoff and Lebel were incredibly important in their recognition that carbon might have a tetrahedral structure, that they were not planar, that here was something which you might have an atom at the center of a trigonal pyramid, and the other atoms would be at the corners of this. Again, there were issues involving things like whether there were inorganic compounds and organic compounds. And when urea was synthesized, it was recognized that organic compounds could be made. You didn't need living systems to do that. An interesting breakthrough for organic chemists, I suppose, is benzene. Benzene, for me, has the same position in organic chemistry that Macbeth has in the plays of Shakespeare. It's a pivotal play about Shakespeare's tragedies, and people look at it as a major sort of turning point in the way that plays and culture moves. I think benzene has the same position because it had a hexagonal structure. It was known to have 6 carbon atoms and 6 hydrogen atoms, but what was its structure? There's a little bit of controversy that has arisen recently, in recent years, in that it looks as though Loschmidt, who was an Austrian, I think, school teacher, who was famous for his work on statistics, really a physicist in some ways, probably came up with the first circular form of benzene. And it looks as though Kekulé actually may have seen the book in which Loschmidt published these structures before he published his own hexagonal structure, which really has become a rather iconic story, in that he tells the story that he thought of this circular structure by looking into a fire and seeing a snake biting its tail. Well, there's no doubt that I think Kekulé's structure of benzene is the correct one, but the circularity of benzene, that it was a ring structure, it looks as though it may well have been Loschmidt who had that idea first, but then was presented in a very interesting way by Kekulé somewhat later.
Il benzene, anche conosciuto come benzolo, è un idrocarburo aromatico ed è costituito da 6 atomi di carbonio e 6 atomi di idrogeno. Con un assetto ad anello esagonale, rappresenta la sostanza aromatica con la struttura molecolare più semplice. Inchiostri, detergenti, fibre con cui vengono realizzati capi d'abbigliamento e tantissimi altri oggetti della nostra vita quotidiana sono tutti prodotti del benzene. Nonostante la pericolosità del benzene sia ampiamente dimostrata da numerose ricerche mediche, per il suo ampio utilizzo questa sostanza è praticamente insostituibile. Molte industrie lo utilizzano per produrre altri composti chimici e viene anche utilizzato per produrre alcuni tipi di gomme, lubrificanti, coloranti, inchiostri, collanti, detergenti, solventi e pesticidi. Il massiccio utilizzo di questa sostanza ha portato ad una produzione mondiale annua che oggi supera i 30 milioni di tonnellate ed è dovuta per la maggior parte alla distillazione del petrolio, anche se una proporzione notevole di benzene viene ancora ottenuta dalla distillazione dell'olio di catrame di carbon fossile.
Now, the interesting aspect of crystals is that they do actually tell us something about the molecules from which they are made. In a sense, the blueprint for the shape and structure and various properties of the crystal actually are laid by the blueprint of the molecule from which it is constructed. And that led to one of the big breakthroughs in chemistry, the development of crystallography by the Braggs, father and son, who got the Nobel Prize for the development of the crystallography. And it's certainly perhaps the most important, until the development of NMR, of a structural method. And of course, led to our understanding of the crystal structure of not just salt, which is a cubic structure. Basically, imagine a cube with sodium at one corner, chlorine at another, sodium at another, chlorine at another one. That was elucidated by crystallography, but it also was used in the development of our understanding of the structure of DNA. Here, one of the most important breakthroughs is actually not too difficult to explain by crystallography. I think there are many different methods of getting the structure of molecules. And my favorite is the one that I use, which is microwave spectroscopy, which we'll come to a bit later. But the development of nuclear magnetic resonance for chemistry, it was a massive breakthrough, because certainly in my lifetime, NMR has become a fantastically powerful way of looking at the structure of molecules. And in the end, I think we now see everything in terms of structures. Again, as I mentioned before, the chemist has this perspective on the world around us, which I think is very different from the average person who doesn't have that feel. We see everything in terms of its structure, and we also see the way it behaves, whether it's a gas, a liquid, or a solid, as something implicitly dependent on the structure, the way the atoms fit together, the way they bond together, whether they're strong or weak, in what way they're organized, and ultimately that's the way that materials are made, and also the way that materials are used in everyday life, in their applications. And so to some extent, chemistry, which I guess subsumes things like metallurgy and material science, is very important to the way that our world has developed, and certainly the technological aspects. It's worth recognizing that when the steam engine was developed, Watt didn't invent it, but he recognized that actually steam was compressible, and he basically made the steam engine efficient by putting a condenser on there. It was first invented by Newcomen about 1700 or so, and it was 60 years before Watt recognized that he could make it efficient by putting a condenser there. But there were no materials. They had leather, or they didn't have rubber, they didn't have plastics. Their engineering was not wonderful. Their steel was difficult. There were all these problems that had to be resolved, and so the development of the modern age really is a materials problem, and that has been solved bit by bit. Today we have some fantastically clever materials, which we'll come to at the end. Aluminium was vital, but of course it was difficult to weld it. That's a material that is much more a late 20th century material in its usage. There were other industrial processes that were important, such as production of sulfuric acid, production of chlorine, production of things like salt and things like sugars, and these were very important in the way that society developed. But one can go back to something really quite interesting in chemistry, and that is the Pantheon in Rome was for maybe 1500 years the largest spanned space, certainly I think anywhere in the world, because the Romans had concrete. The chemistry of concrete was known to the Romans and then forgotten for probably 1.5 millennia until it was rediscovered. And it's interesting to think of the impact on architecture there would have been had concrete, the chemistry of concrete, the recipe for making been remembered. We probably wouldn't have had the Gothic architecture that we have today, particularly the flying buttresses on Notre Dame and these sort of requirements to keep the walls in. There are other very important industrial processes, and I would say in the 20th century, the most important one is the Haber-Bosch process. Because even in some of the underdeveloped nations, the fertilizer is a vital way of producing more food. Estimates vary, but something between 5 and 10% of our energy resources are used to produce fertilizers. 70% of the world is fed by food that uses nitrogen-based fertilizers. So the massive breakthrough that Haber and Bosch made, in which they took nitrogen and hydrogen and passed it over an iron catalyst at about 500 or 600 degrees to form ammonia, which then goes into things like ammonium phosphates and ammonium nitrates. That is basically the chemical process that led to basically the population expansion. Maybe that's not so good, but it's worth recognizing that it dates from that particular point onwards where we were able to feed the world. There are other major breakthroughs, such as Perkin, who developed some of the dyestuffs, and until Perkin, much of the clothing was quite drab because there were no really good dyes and colors. But from then onwards, there was a revolution, and people could have really bright colored clothes. And so there are quite a lot of impact of chemistry that we really have forgotten about because we've assumed they've been always there.
Mendeleev credeva fermamente nell'importanza del progresso scientifico, a partire dall'ambito chimico, per l'avanzamento dell'economia. Senza la scienza non può esserci l'industria moderna, diceva. Per questo, al servizio del suo paese, spende grandi energie intellettuali e fisiche per promuovere iniziative tecnologiche a sostegno della crescita industriale. L'ambito che più lo appassiona è quello delle risorse naturali. Nel 1863 visita la petrolchimica di Bakù, nel Caucaso, e in seguito viene inviato dal governo zarista negli Stati Uniti per studiare da vicino lo sviluppo dell'industria petrolifera. L'industria estrattiva era allora ai suoi albori. La prima trivellazione di un pozzo in Pennsylvania era avvenuta nel 1859 e Mendeleev ne intuisce da subito l'enorme potenza, interessandosi ai problemi dell'estrazione, della raffinazione, della commercializzazione. Naturalmente, da scienziato qual era, si pone anche il quesito dell'origine dei giacimenti e avanza l'ipotesi di una genesi inorganica del petrolio, contraria a quella che si sarebbe poi affermata come egemone nel mondo scientifico, che descrive la formazione del petrolio a partire da materia organica rimasta sepolta in assenza di ossigeno. Con l'invenzione del motore a combustione interna e la scoperta delle sue infinite possibilità di impiego, l'industria petrolifera diventerà una delle basi dell'economia moderna e il più grande business del XX secolo. Eppure Mendeleev, uno dei padri dell'industria petrolifera, metteva in guardia contro lo sfruttamento indiscriminato dell'oro nero. Il petrolio, diceva Mendeleev, è un dono della natura così raro e unico che bruciarlo come un combustibile semplice equivale a un peccato paragonabile a bruciare le banconote. Una preveggenza che pare quasi oracolare nel nostro XXI secolo, in cui incombe l'incubo della fine del petrolio.
I'd like to talk a little bit more about NMR, nuclear magnetic resonance, because the breakthrough by Purcell and Pound, who were interested in the magnetic properties of the nucleus, turned up the effect that it was shifted by other groups in the molecules. There were breakthroughs then by Richard Ernst, who developed the techniques for double resonance and multiple sort of resonance techniques. And this was a major breakthrough. De Gennes had some ideas about this, but Richard really made it practical. That went on to a little bit later, that the development of it as a tool for looking at the brain or body scanning. So MRI, they left off the nuclear magnetic resonance off MRI because people would be unhappy to learn that they were all made of nuclei. So I think that's a bit odd, but nevertheless that's the way it is. Other techniques of importance were mass spectrometry. It goes back to Aston, but later on. This is an incredibly powerful technique in which you can take a molecule and find out what are the constituent atoms. It's basically that of the iron, so there are slight problems, but by and large, it's an incredibly powerful technique that can tell you the stoichiometry of the molecule. And most recent development of very powerful Fourier transform ion cyclotron resonance techniques have allowed us to have the resolution to distinguish between, say, nitrogen, which is 14 mass, and CH2, which is 12 plus 2. My feeling is that the big breakthrough that has come in general for technology is electronics and computers, which have enabled us to make these techniques much more efficient. Without the computers to do the massive calculations that are necessary, it would be much slower. And certainly in my lifetime, computing has revolutionized most of these techniques. But to hark back to an important issue for me, that goes back to photography, it is that the integration capacity of the photographic plate, which was there right from the start, from the middle of the 19th century when photography was developed, Without that, I think experimental science would be 100 years back. I think it's taken maybe 100 years to develop electronic computing integration techniques that can rival the photographic plate. It's not just used for taking pictures of yourself and snaps of these things, but in fact, photographic plates were used to look at the spectrum of the hydrogen atom, to get the spectra of many molecules. And in fact, the spectrum of the hydrogen atom was crucial to the development of theory of physics, and particularly the theory of the atom. Well, chemistry is about making things, and of course synthesis is vital to the whole of chemistry. What I liked about synthesis was that of a complex molecule is that it was a bit like a chess game. Not that I'm a very good chess player. In fact, I'm an awful chess player. In fact, I prefer to do sort of synthesis on a piece of paper rather than chess. But in chess, a move you make now has implications further down the line. And I think it's interesting that some of the synthetic chemists that I know are chess players, and very good chess players as well. Because when you synthesize a compound, you have to think really what the domino effect of your reaction or the sort of step you have made at the beginning might be. And there are not just the steroids, but there are others like penicillin, which have also made a massive contribution to society. Penicillin certainly is one of the most interesting stories, and it relates back to really Fleming, who is very famous for his observation that bacteria were killed by a spore that accidentally came in through the window. He apparently didn't do anything with that. That was around 1930. And when the war effort came along, it was important during the war to actually have an antibacterial. And so what happened there was that by and large, many of the soldiers became infected and they died of the infection. I think it was Flory and Chain. Chain may have actually been the person who suggested that they look at Fleming's observation. That's a sort of magical sort of experiment, which then went on to how to produce more penicillin, and that was developed by Flory and Heatley going to the USA and developing big industrial methods. And by 1942, significant amounts were available, and large number of people really have been saved. Their lives have been saved by penicillin. Probably another compound that is really vital was DDT. And DDT, I don't know, it must have saved 500 million lives. And it's interesting to think about DDT, that the embargo introduced by the Western world has led to something like a factor of 10 increase in the incidence of malaria in places like South Africa and India, and therefore actually condemned about 1 million kids a year to death. Because about 5, up to the age of 5, many children in South Africa are killed by malaria. And I think it's an interesting way to think about the impact of chemistry on society, but also the impact of decisions about how chemistry should be used in society. And holds an interesting point for me to think about in the future, because we know that there are many people who are worried about the impact of the sciences, and particularly chemistry, on the future of society. And so I'd like to read a quotation by Richard Feynman, the great American physicist and fantastic communicator of science. And it was this. It was the atomic hypothesis, which he suggested that it could be stated in a single sentence with as few words as possible. And what he said was this: all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are little distances apart, but repelling upon being squeezed into one another. In that one sentence, there is an enormous amount of information about the world. And that's a very interesting one, because it basically is a qualitative description of the chemical bond. What is it? Well, we have two, say, hydrogen atoms, and as they come together, there's no effect, and as they come closer together, the energy goes down, and as they get to a certain equilibrium distance, there's a minimum, and as we squeeze them further together and further together, we go up to nuclear energies, nuclear fusion. Massively different energies from the chemical bond. The depth of this well from where the two hydrogens are separated to the bottom where they're stuck together, that is the chemical bond. And that is the fundamental aspect of chemistry, how atoms stick together. Now, it's interesting that that sort of diagram, I call it a potential energy diagram, something rather like that was first drawn by Ruđer Bošković, a Croatian stroke Italian scientist, probably some 17 something, where he had a potential diagram to sort of explain the way in which liquids and gases might actually be represented. So in a sense, this particular potential surface has quite an interesting history. Now, an understanding of that bond really required an understanding first of atoms and the way electrons were involved. And what happens as two atoms come together, in cases where the molecules can form, is that there's a build-up. We have an atom with a positive nucleus and an electron with a negative charge going around it. There's a build-up of electron density in the middle, so this negative charge can pull or shield the positive charge from repelling each other. And that really was the essence of the two-electron bond of G.N. Lewis, which goes back to around the 1920s. And the understanding of the quantum mechanics, the theoretical aspects of that, goes back to people like Schrödinger and Heisenberg, and people like Mulliken, who understood that in the case of atoms, we have electrons going around in what's called an atomic orbital, and in the case of molecules, the electrons are moving in what we call molecular orbitals. And that goes back to sort of the 30s and mid-30s. And so it's interesting that by and large, so much chemistry could have been achieved without a lot of understanding of what was going on by the early people. But now the perspective is very different. And it's even different in another way in physical sciences for me, because I look at the work of Willard Gibbs, who developed thermodynamics from a classical viewpoint, without any knowledge of the molecular and atomic aspects of the materials. They were just fluids. One was a solid at one phase, one was a liquid or a gas phase, and produced things like the phase diagrams in which something can move from one phase to another, say from liquid to solid or solid to gas, without an understanding of the deep aspects of the materials themselves. I think the impact of chemistry on biology has been probably one of the most exciting, if not the most exciting one of all. Biology before molecular biology or biological chemistry was really probably could not be considered a hard science. People looked at biology as really a very complex system which perhaps might never have been solved. Of course, Darwin made the biggest breakthrough in a sense by recognizing that the evolution occurred, that some characteristics from one animal were passed on to the progeny. But those were tremendously clever conclusion reached by looking at some very broad and complex sort of observations. Now, I think for me, a major breakthrough was by Avery, who recognized that DNA, nucleic acid, was responsible for the transmission of genetic characteristics. And that was a contentious claim when it was made in the 1930s. But he deserved tremendous recognition for actually claiming this in the first place and showing that it was actually correct. And of course led later on to the breakthrough of Crick, Watson, Franklin and Wilkins in the structure of DNA. One can't talk about the DNA without thinking about the beautiful double helix structure of it. Now, I think when they had the structure of DNA, which is so brilliant and elegant, at a stroke it was understandable how genetic characteristics were transmitted in the most beautiful and elegant way. From that point onwards, I think molecular biology really was a major subject, and I think it will go on in the 21st century to have an impact beyond our imagination. I think no subject has undergone a greater revolution than biology. And of course, at the end of the day, we are now, I think, on the verge of not only understanding how life evolves, but perhaps we will very soon be on the verge of understanding how life actually starts off, from prebiotic sort of soup in which there are a large number of chemicals. Furthermore, with MRI and other techniques, it may be possible to decipher perhaps or understand the last frontier, it seems to me, in the sciences, and that is how the brain works and how we have such fascinating sort of abilities as our sort of understanding and our consciousness, which I think probably, as far as many are concerned, is the last scientific frontier to be passed through. When I started off at school, I didn't know whether I would go on the art side or art, because art was my favourite subject, or science. But I got quite interested in atoms and molecules and making compounds. And at school I got very interested in organic chemistry. But in the second year at university, a spectroscopist, Richard Dixon, gave some lectures on spectroscopy, how light interacted with molecules. And it's interesting to recognize that that is something to do with color. And in fact, let's go even deeper. It was not understandable in the 19th century why things should be colored at all. In fact, more than anything else, color, spectroscopy, was responsible for quantum mechanics. How can I explain that? Well, if I punch you on the nose, and you can't feel it, that's a bit odd, because I can punch you lightly or whatever, harder and harder and harder. But if you punch a molecule with a photon with a given energy, it turns out it has to have the right energy before it absorbs, or it will just pass by. The molecule doesn't see it. It's what's called a resonant effect. If you push a swing, for instance, as you push the swing at the right frequency, the swing will take the energy from you. On the other hand, if you push at some different frequency, it will come back and knock you in the teeth. It will give back the energy. So that resonant effect is very important. And it's related to the quantum mechanics. And it's also related to the fact that you have color, that certain molecules will only have a certain color. So copper sulfate is blue. And we can look at that spectrum and we can tell something about the atoms, the molecule itself, and the way the electrons are bound. We can get structure out of it. And the particular subject that I'm going to talk about is my personal favorite, which is microwave spectroscopy, in which a molecule, as it rotates, and it has a dipole moment, one end is more negative than the other, as it rotates, it gives rise to radiation, or radiation can absorb and interact with that dipole and make it absorb. Now, by looking at the rotational motion and looking at those frequencies, we can determine the structures of molecules, the bond lengths, to very high accuracy. Not only that, there's not just rotational motion, but there's vibrational motion. Now, in the case of carbon dioxide, this vibrational motion can be of various kinds. One bond can expand and the other one can contract, and vice versa, like this. Or it can bend. And those vibrations can interact with radiation. And in fact, the bending and this asymmetric stretching vibration are responsible for the greenhouse effect that we're also worried about. So spectroscopy is important in understanding such things as the greenhouse effect. Not only that, we have molecules such as copper sulfate, which are blue, which these are electronic transitions. That electron is jumping up and down. We can excite the electrons. Classically, we can think of the positive charge and the electron here, and as the radiation, electromagnetic radiation moves along, it'll jiggle the electrons backwards and forwards in a classical way. In a quantum mechanical way, we think of a photon as a particle of energy which comes in and it jumps to an excited state. Now, that has been a very powerful tool. Originally, in the case of atoms, we had the spectrum of the hydrogen atom. It was the spectrum of the hydrogen atom, the way that it interacted with light, that showed a certain type of pattern of what are called lines, which had a certain mathematical relationship. And that mathematical relationship turned out to be quite simple and was worked out by someone called Balmer, I think a Swiss in the sort of 1880 or 1890, who just found a relationship. And a nice story, actually, because Balmer said he'd give him any set of numbers and he'll find a mathematical relationship, if there is one for it. And someone who knew this pattern of hydrogen said, well, I've got this one. And Balmer found the pattern. And that pattern led to Bohr's understanding of the hydrogen atom with one electron, and later on other patterns that led to Schrödinger and Heisenberg elucidating a theory of quantum mechanics which was able to handle multi-electron systems, which of course mainly you have in the case of molecules. So spectroscopy not only led to quantum mechanics, but told us a lot about the structure of molecules. And in my case, I did a lot of structural work and got the structures of small molecules with, say, 3, 4, 5, or 6 atoms in them to very high accuracy. The theory of spectroscopy is also quite interesting because there are lots of interesting things that molecules can do. For instance, methane or ethane can actually rotate. One methyl group can rotate against another, and they can have internal rotation. So it's not only overall rotation and vibration, but there are these internal motions as well. One of the most interesting is ammonia. Ammonia has a pyramidal structure in which you can imagine one nitrogen is at the top of a pyramid and 3 hydrogens at the trigonal base. So this one with the nitrogen here and the 3 hydrogens on this side, the hydrogen can flip over so they're like this. And that's an inversion sort of motion, dynamics. And it's this particular transition that I'd like to mention because it was that inversion transition of ammonia that Charlie Towns used to develop the maser microwave amplifier, and then developed the theory that led to the light amplifier. And so spectroscopy really was responsible for the laser, which of course you use in pointers, or in such things as barcode readers, and of course, more than anything else, in eye surgery. I mean, who could have dreamt that eye surgery could have been impacted by someone who was interested in spectroscopy of a molecule like ammonia? That's a fascinating example of the way that science works. But now we've got more complex systems, such as water clusters. And water is H2O, but in liquid water, the hydrogens are hydrogen bonded to oxygen. There's a weak bond between the hydrogen and the oxygen. Because the hydrogen is highly positive, the oxygen has a lot of electron density, and they stick together. And the properties of liquid water, the crucial properties, in the way, for instance, that the density decreases as water freezes, of course, is vital to the way the seas operate, and that ice stays on the top and fish can still live. If it were not that way, there would be ice on the bottom, and I doubt whether life could have evolved at all. But we now understand that liquid water's properties are very much dependent on what's called a weak bond, okay, this hydrogen bond. And we're now in a position with spectroscopy to analyze these and study these in the gas phase, and water clusters with, say, 2, 3, 4, 5, 6 water molecules all stuck together and undergoing fascinating motion can be understood on the basis of these theories, and we can sort of see now a lot better how water actually behaves in the liquid form. People like Sakeley at Berkeley and others who are working on these weak bonds, Ligon, who was at Exeter, now at Bristol, John Meyer in Basel, are some of the top people at the moment looking at these clusters using the fascinating spectroscopic techniques which have come about recently due to lasers and the development in really fast electronics that computers has brought to us. It's a very exciting time where we now have things like molecular dynamics. We can use molecular beams. People like Yuan Li and Hirschbach and Polanyi have actually studied molecular dynamics. That is, what is actually going on when two atoms come together. That's the intrinsic behavior of molecules at the intermediate between, say, products and the starting materials. And so with these fantastic technological breakthroughs, such as spectroscopy, such as high computing, we can understand a lot more about how atoms actually stick together and can look at the reaction path that Feynman actually said was the most important piece of information to be passed on to the next generation if they didn't have anything at all. I'd like to say a little bit about a subject which I was quite heavily involved with. It is really the development of interstellar chemistry. In fact, one should recognize that the chemistry on the Earth is very unusual in the universe. Most of the chemistry that goes on in the universe is going on out in space. And it's called interstellar chemistry, astrophysical chemistry. It takes place in massive clouds of gas, which we now realize are dispersed between the stars in the galaxy. They're not just the bright stars that you can see, but there are black areas which are so dense that light cannot pass through them. What we've discovered that these clouds are absolutely full of molecules. Townes, again, was involved in this. He developed radio telescope techniques to measure the microwave frequencies of molecules. The first one, ammonia, obviously his favorite molecule. And he detected ammonia in the gas clouds in Orion. I was starting microwave spectroscopy at this time, and I got interested in this and was involved with my colleague Dave Walton and a student Alexander in making carbon chain molecules with nitrogen on the end in the laboratory. And this led to a suggestion to astronomers in Canada that we search for these carbon chain molecules in the space between the stars. We're really excited because we detected them. In fact, we detected 3 of these molecules and longer chains. This was with my colleagues Takeshi Oka, Lorne Avery, Norm Broughton, and John McLeod. It was a very exciting time around the mid-70s. Then another breakthrough was made by infrared. Infrared techniques were being developed, very sensitive techniques, and one could see stars called infrared stars that you couldn't see optically. So these gas clouds, which were quite dense, coming out of some stars, actually hid the star, but the infrared could get through. And that led to some microwave studies which showed that these carbon chains were coming out of stars. At the time, there were 2 theories of the way these molecules were formed. Now, these looked like 2 very good theories which seemed to fit our observations, but they did not fit ours on the carbon chains. The chains were just too big. But they were coming out of these stars, and so I suggested that we look at a third process, was that of what were the processes in a carbon star that were taking place. And that led to a suggestion of an experiment with Rick Smalley, who had developed a fantastic technique for looking at clusters. It's cluster beam technique, in which you take a laser, vaporize a metal, say, and look at the metal clusters that come off the surface. And in discussions with Rick about his technique, it seemed to me that this was the ideal technique for looking at what was going on inside a carbon star. Well, the rest is all history. Basically, what happened there is we vaporized carbon instead of a metal, and off came not only these carbon chains that we detected, but what we now call, or kids call, the buckyball. Well, I called it Buckminster Fullerene, and it's this beautiful molecule which has the same pattern as a soccer ball with 12 pentagons and 20 hexagons. What happened was we vaporized graphite, and we came up with this very strong mass spectrometric signal for something with 60 carbon atoms. I'd been to Expo in 1967 and been quite fascinated by Buckminster Fuller, his dome and his work. I didn't even contemplated going to work for him. Rick had also been there, and so we got the book, and also I'd made a star dome for my children, which turned out to have the right structure. And with these clues, we were able to draw a conclusion that maybe this structure explained why 60 carbon atoms was special. When you threw them up, almost like magic, they would form this incredibly beautiful symmetric molecule. That was a big surprise. In fact, about half a dozen papers were written after we published it to say that it wasn't correct, but it turned out it was. The 21st century buzzword, nanotechnology, or what I like to say, nanoscience and nanotechnology, N and N. What is it? Well, there are many definitions. It's not just something that's very small, nanoscale, 10 to the minus 9 of a meter. No, it's chemistry. That's what molecules are. And there are various aspects of it, but I think the best ones for me would be atom by atom, molecule by molecule, assembly of a complex system by bottom-up process. By that definition, Human beings are the results of nanoscience and nanotechnology, because we have been made atom by atom, molecule by molecule, and we've been built up from the bottom up. Top down is the way that our computers are made, our chips. We take silicon and then we produce these wonderful structures on the surface, and that's top down. Another aspect of this is that by sort of bottom-up assembly, if we have the control, real control, accurate control, that, say, DNA has over constructing us, then we should be able to produce really super materials. Many of you may have heard of carbon nanotubes. They're exciting materials, but we only have them in very small amounts, and we don't have very good control over the quality. What do I mean by quality? That the diameter and the length. If we had very accurate control over the diameter, okay, so we could produce a bundle, all the same diameter, and say a meter long, we could create the most wonderful material for civil engineering. We could build, say, bridges that would not fall down in earthquakes. There would be a material maybe 50 times stronger, effectively stronger than steel, and maybe 1/6 the weight. Now, why do I say that? Well, materials are don't have their intrinsic strength. Actually limits things like aluminium or iron or steel. It's not the intrinsic strength of the bond between the iron atoms, but the fact that there are defects in there that can be exploited to crack the material. What's an example? If you have a tree and you want to cut it down, you saw a little sort of saw cut in it, and then you push it over because you put all the effort, all the force at that weak point. With nanotechnology and perfection, and particularly with carbon nanotubes, it should be possible to overcome that aspect. In a sense, that's the way wood works. If you know, wood is very easy to break along the grain, but against the grain is much more difficult. We should be able to do that with nanotechnology using these nanofibers, but it's a very big problem. I don't know how to solve it to get the sort of efficiency and high quality required to exploit the ultimate material, which I think would be the carbon nanotube.
Tutte le parti del nostro corpo, anche i più minuti dettagli, sono il risultato di reazioni biochimiche che nella maggior parte dei casi necessitano di una fonte di energia chimica. La maggior parte dell'energia utilizzata in qualunque momento dall'organismo proviene dal nucleotide adenosina trifosfato, conosciuta come ATP. L'ATP è la sostanza in cui le cellule accumulano temporaneamente l'energia necessaria a sostenere la loro attività. La quantità di ATP contenuta in una cellula è piccolissima. Il corpo umano, complessivamente, dispone di una quantità di ATP sufficiente a sostenere le sue attività per appena 20 secondi. La riserva di ATP, quindi, deve essere continuamente ricostituita. L'ATP reagisce spontaneamente con l'acqua, liberando energia e alimentando praticamente tutti i processi dell'organismo. Con l'idrolisi, la reazione dell'ATP con l'acqua, l'ATP perde una molecola di fosforo e genera ADP, adenosindifosfato, che come dice il suo nome contiene solo 2 gruppi di fosfato. Ora, un apporto di energia esterno permette a una molecola di ADP di legarsi a un gruppo fosfato, formando una nuova molecola di ATP. A sua volta, poi, la molecola di ATP cede un gruppo fosfato e si trasforma nuovamente in una molecola di ADP, liberando altra energia utile per le cellule. Con il ciclo ATP-ADP, le cellule dispongono di un sistema continuamente ricaricabile per conservare energia e per trasferirla laddove l'organismo ne necessita. L'entità del processo di produzione e consumo dell'ATP è sbalorditiva. Anche quando una persona sta a letto in totale riposo per 24 ore, le sue cellule consumano e reintegrano circa metà del peso corporeo di molecole di ATP solo per alimentare i normali processi di sostentamento.
The other aspect of nanoscience and nanotechnology really goes back to things like molecular biology. And I think the exciting areas there are what I call molecular machines. In biology, Max Perutz obtained the structure of hemoglobin, which is an amazingly sophisticated little molecular machine. It grabs oxygen in the lungs where there's plenty of it, theoretically, if you're still breathing, and passes it to where you need it in your muscles and where it's used to convert food and oxidize the food and produce sort of ATP, adenosine triphosphate. Now, what's that? Well, ATP is adenosine triphosphate. T is tri. And this is produced from adenosine diphosphate, ADP. And the amazing thing is that John Walker and Paul Boyer showed that ATP, ATP synthase, the enzyme that produces ATP from ADP, is an electric motor. And for me, that was a revelation. I remember going to John Walker's lecture when it been announced that he won the Nobel Prize. I thought, well, I'll go and look to this. And I just almost fell off my chair. Here, life had invented a molecular machine, an electric motor, not driven by electrons, but driven by protons in aqueous solution zillions of years before Faraday had developed his electric motor. They're already there. And now that we know that these motor enzymes are absolutely crucial throughout the body. In fact, human beings produce about half their body weight of ATP every day, and an athlete may be more than double it if they have a lot of long distance running. My view is not only do we need accurate control of materials, but in the future we will be making molecular machines, sophisticated machines for medical purposes. And in fact, viruses that people like Aaron Klug and Casper showed had some structures very similar to the buckyball. These are very clever enemies. And I think in the future, we'll recognize that the drugs which we've had today, like penicillin, are very simple compared to the enemy that they've had to fight. We need to develop clever molecular systems that can recognize what they're looking for and also can combat them. And I would suggest that nanotechnology, which for me is only a new name for 21st century chemistry, or chemistry with a bottom-up self-assembly perspective, will be the age of molecular machines, hopefully used for the benefit of mankind rather than to its detriment. I was once in a BBC discussion, and one of the people opposite me said life would be a lot better if there were no technology. And I said, do you really believe that? I mean, half of all children died by the age of 8. Children with malaria, many died by the age of 5. And he just said yes. Well, I mean, here was a guy who was just living in a studio, and all this technology around him. So I just thought, well, I thought he was stupid. But there are issues that need to be understood. They're humanitarian issues, and chemists have made contributions, very positive ones, such as anesthetics. I mean, you go back to the drawings of Rowlandson to the 18th century to see what it was like to have an amputation without an anesthetic. They didn't have mobile phones to see what must have been unbelievably horrific scenes, and that must have happened really quite regularly. There can be no more humanitarian contribution, it seems to me, than anesthetics to society. DDT, as I mentioned, probably saved millions of lives. Penicillin similarly. So I think there's no doubt there have been massive humanitarian contributions, but there have been some negative ones as well. I can think of napalm. I just feel that that's not what chemists should be making. If you're a physicist, you shouldn't be making better atomic bombs, more effective napalm, and if you're an engineer, more effective landmines. For me, that's not science. That's a distortion of science by society, by people who I do not think are doing the science for humanity. I can understand issues, but nevertheless, these are issues that bother me about the impact of our discoveries made by the scientific community on the way society behaves, which does not seem to be able to solve its problems without using technology to kill other human beings.